Welcome to Spring LIB.
Hello everyone, today we're doing chapter 19, problem 16, and this problem asks us to rank the compounds in each of the groups in order of increasing acidity. And just like how we did in problem 14 of this chapter, we determined that the better acid is going to have the more stable conjugate base. So what does that mean? That means that when it loses its proton, its conjugate base is going to be stabilized either by putting a negative charge on an electronegative atom or by stabilizing the negative charge through resonance structures, having multiple resonance structures and such that the negative charge will move onto different nucleuses throughout the molecule. So if you look at A, we see that we have this acetic acid. We have this other type of acid here. Then we have another acid here. So we see that obviously the proton that's going to be lost is the most acidic proton, being the carboxylic acid proton. And what happens is that once it's lost, we're going to have a negative charge on this oxygen that can be stabilized through resonance for all three of these. So all three of these will have the same level of resonance stability. But what happens after that? So what we need to investigate is that now, because for all of these, we will have a negative charge on this electronegative atom, and then we can have a resonance stabilization forming two resonance bonds or two resonance structures with the negative charge on this oxygen atom. We need to investigate other factors. So what else can make this proton more acidic? Well, the proximity of electron withdrawing groups or electronegative atoms can pull electron density away from the hydrogen nucleus towards its own nucleus, and thus making this proton more electron poor and susceptible for abstraction by either bases or nucleophiles, so it can be easily ripped off, more easily ripped off. So if you see in this molecule, we see that we have this carboxylic acid, we have this alcohol. So this alcohol, being oxygen, is electron withdrawing. So we can say that we'll have electron density being pulled towards this alcohol nucleus, making this carboxylic acid less electron rich, and therefore making this proton more susceptible to abstraction or to being ripped off, and therefore making it more acidic. So not only that, but having this electronegative atom in close proximity to the conjugate base will also stabilize the conjugate base, because not only is the conjugate base going to be stabilized by two resonance structures having the negative charge on this oxygen or on this oxygen, but now some of that electron density of that full negative charge can be shared through inductive pull of electron density towards this alcohol group here. So we know that oxygen is more electronegative than sulfur. So we know that the pulling effect of this molecule is going to be greater than this molecule, even though they're the same number of carbons away. So we can say out of these two, this molecule is going to be more acidic because it has a more stable conjugate base. So we can just say this is going to be the most acidic. Now, sulfur is not really that electronegative. So actually, sulfur with its lone pair electrons might actually donate electron density towards the conjugate base, and actually it will form kind of a negative charge over here, and we'll have a negative charge up here. So we have two like charges in close proximity, so it's not that favorable. So we can actually say that even though there will be electron pull of electron density towards this sulfur atom, there might also be some opposing effect that might occur, but it's not really likely. So we'll just stick our discussion to the electron effect of the sulfur group, the electron pulling effect of the sulfur group, of the thiol group, to stabilize the conjugate base. So now we have to determine what is going to be the second and the lowest level of acidity. So if we look at the remaining two options, well, we have this acetic acid and we have this acid here. So acetic acid, what is it stabilized by? Well, it's stabilized by two forces, having negative charge on an electronegative atom, such as this oxygen, and moving this negative charge onto this oxygen over here, so it has resonance structures. But there's no actual pulling of electron density anywhere else, unlike this one here with the sulfur. So we can actually say that this is going to be the least acidic, making this one with a thiol group more acidic than acetic acid. So this is going to be the least acidic, leaving this thiol as intermediate acidity. So now if we move on to B, if we draw the molecules in B, so we see that something similar happens in B as in A. So we're interested in the most acidic proton. So this proton is going to be ripped off. That's going to leave a negative charge on this oxygen atom. So we have a negative charge, an electronegative atom, which is favorable. But now also this negative charge can be resonance stabilized by moving the negative charge to the oxygen atom on the top. So all three of these will have negative charge that is going to be resonance stabilized and is also going to be stabilized by having the charge on an electronegative atom. So far it's a tie. So just like in A, now we're going to look at the electron pulling effect or the inductive stabilization of these conjugate bases by proximity of electron withdrawing groups, or we could say by proximity of electronegative groups. So we have iodine in this example. So if you look on the left, we have 2 carbons away, so we have the carboxylic carbon and this alpha carbon. 2 carbons away, we have 1 iodine. The middle one, 2 carbons away, we have 2 iodines, and the third one, 3 carbons away, we have 1 iodine. So obviously something that is going to have more electron withdrawing groups, so 2 iodines closer together, is going to be having the most electron density pulling effect towards the iodines, and therefore is going to stabilize the conjugate base to the most degree. So we can say this middle one is obviously going to be the most stable. But now what about these two? These two each have an iodine. They have 1 iodine. The difference is that there's 1 carbon separating them. So obviously something that has the electron withdrawing groups closer in proximity will cause a greater effect than being further away. So this one that's now 3 carbons away is going to be least acidic compared to this one that is just 1 or there's just 2 carbons away. So we can say this molecule is going to be the least acidic, and this molecule here is going to be the intermediate acidity. This is all due to the stability of the conjugate bases.